tomorrow will be better. On the board here, we have some water here, and we are told that a piece of wood is partially submerged in the water as shown. And here's the information we have about a piece of wood. We got here the density of the piece of wood, which is 600 kilograms per meters cubed. Next is the volume of the wood, which is 0.5 meters cubed. And here comes the question. What portion of the wood is submerged? A lot of you say, but teacher, we've been given the volume of the wood. So why did they say ask for the portion? Because talking about portion, we are referring to the volume. Take note that here is the volume of the entire piece of wood, but not the entire piece of wood is submerged in the water. And a very important detail to observe here is the fact that this piece of wood has been said to be floating. It's floating, it's not sinking, it's not under the surface of the water. All right, so follow me there, friends. Let's solve this very quickly. Solution. In this problem, we are going to be applying a very important principle in physics called the Archimedes principle, according to which every object like this one, which is either partially or fully submerged in water, experiences what we call a buoyant force, which is equal to the weight of the displaced fluid. All right, you can comment down there in the comment section if you still have problems with applying this principle. All right, so I'm going to go step by step and show you how to answer this question. All right, let me start by writing down some sort of a resolution of forces on this object. This is the object here. There is first of all a downward force here, which is the weight of the wood, and then there is the upward force here, which we call the buoyant force. All right, now since the question tells us that the piece of wood is floating, we are going to write a very important equation here. If the piece of wood is floating, then the weight of the piece of wood should equal the buoyant force. All right, and according to Archimedes' principle, this buoyant force should be equal to the weight of the displaced fluid. We will denote it like this, the displaced fluid, which in this case is water. All right, so in all of what I'll be doing after this, I'll just be simplifying the two sides of the equations, and you will notice that at some point, clearly and automatically, we are going to obtain a certain quantity here, which will be actually the volume of the water displaced. And coincidentally, this volume of water displaced is exactly equal to the portion of the wood which has been submerged in water. At this point again, I will say, if you have problems on how to go about this, like if you don't really understand how it's possible that the volume of water displaced is equal to the volume of the object which has been immersed, or the portion of that object which has been immersed, you can always write it down in the comment section and I'll do a special session for you. All right, on the left side of the equation, what am I going to have? What's the weight of the wood? Weight, as we all know, weight is equal to the mass times the gravitational acceleration. But we do not know the mass of this log of wood. All right, all we know is its volume and its density. But we know that mass can be also expressed as the product of the density and the volume. All right, mass can be expressed as the density times the volume. So in this case, we are going to have here that where we have the wood, the weight of the wood, we would say this implies, instead of writing weight of the wood, I'm going to put here density of the wood times mass, or rather times volume of the entire wood. All right, and then times gravitational acceleration. On the left side here, I've written the expression for the weight of the entire log of wood. This should be equal to, now look at here, this is very delicate here, dear friends. The weight of the fluid displaced. Be careful, not the weight of the entire fluid. Okay, we are not asking for the weight of all this water here. We are asking for the weight of just a small portion of water which has been displaced. All right, which again, like in the case of the wood, will be equal to mass of the water displaced times acceleration due to gravity. But we do not have the mass of the water displaced. But again, we can also express the mass of the water displaced as a product of the density of the water displaced times the volume of the water displaced. Alright, so let's start by writing this down. So the weight of the water displaced, WF, will be equal to the density of the water displaced, the volume of the water displaced, times the gravitational acceleration. Now we're getting to more interesting things here, dear friends. Take note of something here. The volume of the water displaced is actually equal to, like I said in the beginning, the portion or the volume of the wood which is submerged, because the wood submerged will only displace as much space as it requires, or as much space or volume as it is. In conclusion, the volume of this portion of wood immersed is equal to the volume of the water displaced. So we will write that important note here. We say, but volume of the fluid displaced will be equal to the volume of the wood immersed. I will write WDE, or submerged. And this is what we are looking for. All right, so if I recapitulate and write everything down, I'm going to have that. Therefore, the weight of the wood, which is the density of the wood, times the volume of the entire wood, and times gravity, will be equal to the weight of the fluid displaced, which is equal to the density of the fluid displaced, times the volume of the fluid displaced, admit this for now, and then times gravitational acceleration. Clearly this and this will fall off, and to make VF the subject here, we will have that VF, volume of fluid displaced, will be equal to the density of the wood, the entire wood, times the volume of the entire wood, all divided by the density of water, the fluid displaced, which is water in this case. Therefore, if you carefully punch in your calculator, you will have that here we have 600 kilograms per meters cube, here we have 0.5 meters cube, and then here we have 1,000 meters cube. You're wondering where 1,000 is coming from. This is the density of pure water, all right? It's 1,000. It's most likely or very approximately equal to 1,000 kilograms per meters cube. And if you punch this correctly, you're going to have that this will give you 0.3 meters cube. Now, let me explain something here. This 0.3 meters cube represents the amount of water which is displaced the moment this portion of this log of wood is immersed here. Therefore, the volume of submerged log of wood, which is equal to the volume of the fluid displaced, is equal to 0.3 meters cube. Now the question asks, what portion? All right, so portion would be equal to the small portion, the small part of it which has been submerged, divided by the entire volume here, which is nothing else but 3 feet of the total volume. All right, so 3 feet of our log of wood is submerged in water. If you have problems applying Archimedes principle, leave it in a comment section and I'll do a special session for you. Share this video because tomorrow will be better.